Hi all. In this video we are going to see a basic system architecture of a Linux machine. This is a very first diagram I got from Google when I searched for Linux system architecture. Uh, I don't think why somebody has put shell here. Probably system libraries will be more correct here. So what does the diagram means? At the very core of a machine comes the hardware, and the hardware is surrounded by the kernel, which is the Linux operating system, and next comes the system libraries, and at the very outer core of the architecture comes the application. It means for any application to access the hardware, it has to go via the system libraries and then the kernel. To understand it better, let's take a simple hello world program. Let's compile and execute this one. It just prints the string hello world. This program uses two hardwares. One is the CPU and other one is the monitor, where you can see the output. We will see how the code gets into the CPU in some other chapter, but right now we'll see how the access to the monitor happens. We have a nice utility called ltrace, which will tell us what are the system libraries a process uses. So let's run the same code with ltrace. So puts is the one which is being called with the argument hello world. So somehow it come to the monitor, but from where the puts came? If you see the code, we didn't use the function puts at all, but actually what happens is printf is not a function, it's a macro which is wrapper around puts. So when you call put printf, actually we are calling the puts function. Okay, so the code, the application uses system library to get into the hardware, but where comes the kernel here? Let's look into that. So we have another utility called strace, which is going to tell what are the system calls an application uses. Strace. This application uses this many system calls. Don't worry about all the system calls till this level. These are necessary system calls to start an application. We have to worry about only this system call, write system call. So if you see the argument, the first argument is 1 and the second argument is a string which you wanted to print. So if you see the application to access the monitor, it is calling a library function which is putters, and putters internally calls the system call write, and it is passing the string all the way down to the kernel, and somehow kernel sends it to the hardware. Man page of the write system call says the first argument of the write system call is the file descriptor. So how come writing to a file makes the content appear in the screen? So to know that well, we will try to see what the file descriptor is actually pointing to. Right now our code executes very faster. Let's make the code run little slower. So in the meantime, we can go and identify what the file descriptor is actually pointing to. So let's add a delay to our code. Let's compile and execute this code. Let me suspend it. The PID for the program is 20975. We will try to see what are the file descriptors opened by this particular process. So for that we have a utility called lsof. You pass the PID 975 and you'll get all the file descriptors opened by this particular process. So we are interested on the file descriptor 1, which is actually pointing to the file dev/pts/19. What is it actually? pts19. This is actually a character device. Probably this is a device node created by the Linux kernel, and internal Linux kernel maps the device to the monitor. So whenever an application tries to open the file and writes anything into the file, that will come on the screen. To verify that, let's do that from our code only directly. Instead of simply using a printf, let me open the file here and then write the content into that file. Let's compile and execute the code. So you can see the content came to the screen. So it means this is the device node which is actually connected to the monitor. I mean, what does this mean? The kernel which is protecting the hardware provides a device node for the application. So whenever the application wants to access the hardware, it will access the device node like a file, and it can do all the operations on the file, and that will be internally emulated by the kernel to a hardware operation. The world would be a better place if everybody starts following the rules, but that's not the case. So what if I have a program which tries to directly access the hardware? Let's just do an experiment. I have code which is going to read the CR0 register. Inline assembly code actually tries to move the content of CR0 register into the general purpose register called RAX, and this line we are printing the value in the RAX register. CR0 register in Intel CPU is a privileged one, so an application shouldn't able to access CR0 register. So let's see what happens when we build and run the code. The application got killed with the segmentation fault. Let's see in a moment why the application gets killed. But before that, let's try to run the same code from the operating system. So to run a code as part of the OS or the kernel, we need to write a module. So I already have a module. This is my module code. I will create a separate video on kernel modules, but right now just imagine having a code in the module and loading the module into OS will actually run the code as part of the operating system. So this again tries to move the content of CR0 register into the variable x11, and this x11 value is going to be printed by this print k line. Usually module outputs are not going to be printed in the console. Module outputs can be seen using the command called dmessage. So let's start watching the dmessage output. So for that we have to run dmessage with the option W. Now let me build and load the module. After building the module, I'll get a KO file, which is a kernel object. So this file can be loaded into the kernel, and when it is getting loaded into the kernel, it will be executed as part of the kernel. Yeah, you can see the content of CR0 register gets printed in the dmessage output. So you do the same operation accessing the CR0 register in an application, but the application gets killed. You do the same operation in the kernel. It runs without any problem. What is the difference? Here comes the hardware feature called CPU privilege level. Recent CPUs are coming with at least two CPU privilege levels. One is supervisor mode, the other is normal mode. In supervisor mode, all the instructions are allowed to run. In supervisor mode, all the hardware can be accessed. There are no restrictions. But in normal mode, some privileged instructions are not allowed to run, and hardware access is very much limited. Any violation by the program running in the normal mode will be notified to the program running in the supervisor mode. This feature is exploited by the kernel, and kernel puts itself into the supervisor mode and always runs the application in normal mode. So in our case, the getCR7 program, which is running in normal mode, when it is trying to access the CR0 register, the CPU notifies the kernel about the suspicious activity, and kernel finds that as a malicious one and kills the program. But when the same code getting executed as part of the kernel, as the kernel is already running in supervisor mode, the CPU doesn't complain anything and it simply executes the code. As a summary, in this video, we have understood the theoretical part of the Linux system architecture, how the hardware is protected by the kernel, and we understood how the Linux implemented this system architecture by bisecting a simple hello world program. At the end, we understood the privilege level of CPUs and with that help we understood what will happen if an application misbehaves. Thanks for watching the video and subscribe to our channel for future videos.